In this video, I'll talk about how to calculate the expected values of discrete random variables. Some important terminology in this section includes the mean, or the expected value of a discrete random variable x. The mean measures the center of the probability distribution. So the expected value formula is given at mu is equal to E of x, which stands for the expected value of x, and that is equal to the sum of x times the probability of x. Expected is a mathematical term which is the mean of the probability distribution, or measure of its central tendency. The variance of a discrete random variable x is the measure of the distribution around an expected value. We'll be using mu because we'll talk about populations. The formula that we're using for variance of a discrete random variable is sigma squared is equal to the summation of x squared times the probability of x minus mu squared. Remember, mu represents the expected value or mean, and sigma is our standard deviation, but when it's sigma squared, that is variation. For standard deviation, we'll simply take the square root of our variance. So sigma will equal the square root of sigma squared. Another thing that will be useful to us is Chebyshev's rule for discrete random variables and the empirical rule for discrete random variables. In the table below, you can see a reminder of what percentage of the data is expected to fall within 1, 2, or 3 standard deviations of the expected value. So knowing the mean and the standard deviation of the probability distribution of x, we'll be able to make a statement about the likelihood of values of x falling within 1, 2, or 3 standard deviations of the expected value. So in the chart we have just a reminder of those percentages. Chebyshev, remember, within that first standard deviation we don't know much about it, but it is more or equal to 0. So we'll refer back to this chart with an example for our classwork today. Today's reference for classwork is about marketing age. What is the age distribution of promotional sensitive shoppers? A supermarket super shopper is defined as a shopper for whom at least 70% of the items purchased were on sale or purchased with a coupon. In the table you can see that we're given age ranges in years and the midpoint in years. So the midpoints are found by taking 18 plus 26 and dividing by 2. That makes the midpoint age of shoppers 22 years. The reason why we want to have midpoints included in this table is so that we can later interpret what percent of the data falls within 1, 2, or 3 standard deviations from the expected value. And we'll be using the midpoints to do that. In the table we're also given the percent of super shoppers. Notice it says percent, not probability. So we'll need to change these percentages into probabilities. Part A is asking us to use the age midpoints and the percentage of super shoppers. Do we have a valid probability distribution? In order to be a valid probability distribution, we'll need to make sure that each probability is greater or equal to 0, and the sum of the probabilities needs to add to 1. So in the table I'm going to convert each of these percentages into probability. So 5% would be 0.05, 34%, 0.34, 28%, 0.28, 15% is 0.15, 11% is 0.11, and 7% is 0.07. And this is the probability of x. So all of those probabilities are positive numbers. They're all greater or equal to 0, so they pass that criteria. And if I add all of these probabilities up, it does equal 1. So we can answer yes, this is a valid probability distribution because each probability is greater than or equal to 0. And the sum of the probabilities is equal to 1. And finally, each event is distinct. In Part B, we're going to draw a histogram to graph the probability distribution. So the probabilities will be the vertical axis, and the midpoint age in years will be the horizontal axis. The midpoint ages we have are 22, 31, 40, 49, 58, and 67. Looking at the values for probability, we have from 0.05 up to 0.34. So maybe a scale in tenths would accommodate all of our numbers. So now that we have our scale, we're ready to draw the bars. The midpoint age of 22 goes to 5. 31 is at 0.34. 40 is at 0.28. 49 is at 0.15. 58 is at 0.11. And finally, we've got 67 is at 7. And there we have our histogram. Again, it's up to you if you would like to write what percentages fall at the top of each of these bars. If you wanted to write in 0.05, 0.34, 0.28, 0.15, 0.11, and 0.07. That just makes it easier to read and interpret the histogram for later use. For Part C, we want to compute the expected age, which is mu, of a super shopper, and then we'll interpret the result. Well, the formula for the expected value is to sum the x times the probability of x values. So if we were to construct a table, that would help us to organize all of the information, and then it would be also helpful from there to calculate the standard deviation. Since we need x multiplied by the probability of x, we were given the age and midpoints, so from 22 down to 67, those are the x values. And then the probability of x has been written here in the table as well. So now all we need to do for the x times p of x is multiply 22 times 0.05, 31 times 0.34, and so on. Now we have all of our values filled in, and we're going to sum those values, and that is our expected value. So mu is equal to the sum of xpx, and that is 41.26. Now it's also important to know, what does 41.26 represent? Well, it does say that it's expected age, so this must be age in years. So the average age, or the expected age of the super shopper, is 41.26 years old. Now you see we have some other columns in this table to fill in, and that will help us to find the standard deviation. In order to calculate the standard deviation, we need the x squared value, and then we'll take that x squared and multiply it by the probability. So let's fill in the x squared values. 22 squared makes 484. 31 squared is 961, 40 squared is 1600, 49 is 2401, 58 squared is 3364, and 67 squared is 4489. Now we're going to take that x squared value and multiply it with the probability of x. So we're taking 484, multiplying by 0.05, and that will fill in the product. So our calculations, x squared times the probability of x, we've got 24.2, 326.74, 448, 360.15, 370.04, and 314.23. So we're going to fill in some of our values here to make this substitution a little smoother. We notice that the variance, x squared, needs to be calculated before we can find the standard deviation. And the variance involves the product of our x squared times the probability, but we do need to find the sum. So we will add up that last column, find the sum, and then we have subtraction of mu squared. That is the expected value squared. So we found already in Part C that the expected value is 41.26. So to find mu squared, we simply take 41.26 and multiply it by itself. That comes out to 1,702.3876. When we find the sum of our last column, x squared px, that comes out to 1,843.36. So to find the variance, we'll be starting with that sum of x squared px and then subtracting u squared. That makes 140.9724. Now to find the standard deviation, we simply take the square root of 140.9724, and that is about 11.87 years.